In this video, we will talk about KSP. KSP is an equilibrium constant that has to deal with what is known as a sparingly soluble solid. So we have solids here, but sometimes when you have a reaction that forms a precipitate, such as silver bromide here, you don't always get 100% precipitate. In fact, many times the AGBR or any types of what we will call sparingly soluble solids are in an equilibrium. They're at an equilibrium with its component ions, such as Ag plus and Br minus for silver bromide. So that's what's called a sparingly soluble solid. So in that equilibrium, we have a KSP. It's just like the other capital K's equilibrium constants that we've studied before. The only difference is that we have the subscript SP, which stands for solubility product. So the solubility product constant, like any capital K, is products over reactants. So here, remember, we never put solids in our equilibrium expression. So for silver bromide, it's going to be the concentration of Ag plus times the concentration of Br minus. And that has to equal to KSP. So remember, KSP is quoted at a specific temperature. In this case, we looked it up at 25 degrees, and it to be 7.7 times 10 to the minus 13. So it's a very, very small number, which really tells us just by the magnitude of the KSP that most of the equilibrium resides predominantly in the AGBR solid form, the left-hand side, but some of it is going to go in this direction, very little, but some of it will go in this direction to give us Ag plus and Br minus. So remember, it's not 100% precipitate. Some of it goes back in solution to its component ions. So here's a listing of some different solubility product constants. You can see here that all of these are solids that are in equilibrium, back and forth arrow, with their component ions. And a lot of these are very small numbers. So for example, silver bromide, as shown in the previous example, 7.70 times 10 to the minus 13. Here we got 10 to the minus 23 for zinc sulfide. So all of these KSP equilibrium constants are exceedingly small. So the equilibrium will primarily favor one side, and that's the side that contains the solid. Some of it will go to the right-hand side to make ions. And don't forget, we always quote the equilibrium constant, in this case KSP, at a specific temperature. Equilibrium constant is products over reactants. These are solids, so they will not go into our equilibrium expression. Remember, solid. So like all equilibriums, we have to use an ice table. We don't concern ourselves with AGBR because it's a solid, but like we said, some of it is going to go in this direction, and instead of X, which is typical for an ice table, what you saw for acid-base equilibrium reactions, we're going to use S, and the S here stands for solubility. As before, we will have our equilibrium expression. We don't add solids, and so we look this value up, 7.7 times 10 to the minus 13. We'll put in our values here for S for Ag plus and S for Br minus, and we'll get S squared. So the solubility for silver ion and bromide ion, again here you want to put your units, is 8.77 times 10 to the minus 7 molar, which is moles per liter. So this is the approach that you will use to solve KSP problems. Don't forget situations where, as an example, lead 2 iodide, the lead has a transition metal, so we have to designate its charge. This as an example of a sparingly soluble solid that's at an equilibrium with lead plus 2 and I minus. So I want to bring to your attention that we have to balance this, so we have 2 I minuses. So it's mass balance because we have 2 I's and 2 I's on the product and reactant side, 1 PB, 1 PB. Also want to convey to you that it's charge balanced. So we have a plus 2 on the PB, we have a minus 2 on the I, so plus 2 minus 2, 0. So 0 on the reactant side, 0 on the product side. So this ice table is going to be a little different than the one before. In this ice table, we're going to have plus S and then plus 2S. So the 2S comes from the fact that we have 2 I minuses. So plugging that into our equation for equilibrium equation for KSP, it's going to be I minus squared, right? So I want to bring your attention that the square comes from the fact that we have two I minuses. So we put in, we're going to put in the S for PB plus 2. We're going to put 2S now for I minus, and plugging that in, here's the KSP constant that I got from the book at 25 degrees. And so plugging those values in, we have 4s cubed, s for PB plus 2, 2s for I minus. We square it, excuse me, once again, because that is the definition of the law of mass action. And so now solving for S here, we get this concentration of 0.00151 as our solubility S. So the solubility S for lead is 0.00151. For I minus, remember, we calculated it to be 2S because there's 2 moles that this forms as this solid disintegrates. And so the solubility is going to be 2 times that, which is 0.00303. Don't forget to always put in your units. The units here for solubility are in molar. So we're going to have a solid PbI2, but some of that is going to go in the opposite direction to give you pretty dilute amount in water of 0.00151 lead that's dissolved in water and 0.00303 I minus that's dissolved in water. Finally, we have something called the common ion effect. So the previous examples were done in the presence of pure water. What happens if you take this lead iodide, lead 2 iodide, and let's say dissolve it in lead nitrate, whose concentration is 0.20 molar. And for this specific example, lead 2 nitrate, all nitrates are soluble. So the lead 2 nitrate is nothing more in water is lead plus 2 and nitrate. So we're not going to concern ourselves with the nitrate because it's what's called a spectator ion or a common ion. But I want to bring your attention to the fact is, you see the KSP, which we looked up in the book, is very small at 1.39 times 10 to the minus 8. So any type of reaction that goes in this direction to give us the ions, very little of it is going to come from the reaction going to the right-hand side. Very little of it is coming from the reaction going in this direction. Most of the lead plus 2 that's dissolved is going to come from the lead 2 nitrate. So here, when we do our ice table, we still have our customary S, but we also have in green 0.20 molar from lead plus 2, which comes from the lead 2 nitrate, which again, all nitrates are soluble. So we're going to plug that in, 0.2 plus S into Pb plus 2 concentration. Don't forget the I minus gets squared. The I minus gets squared because we have 2S from the 2 moles of I minus. Plugging all those in here, what we can do is make a low ionization assumption. So here what I'm trying to say is that you see the S is going to be very small. So since the S is very small, again, the magnitude of this 10 to the minus 8 is so small, very little of it is going in this direction. So most of the lead plus 2 is going to be 0.20 molar. And we can still solve for S. And so this is essentially the low ionization assumption, also known as the common ion effect. Most of the Pb plus 2 is coming from the common ion, which is given to us by the 0.20 molar lead. Once again, the nitrate is a spectator ion. So making that simplification, we have 0.2 times 4s squared. 0.2 times 2 is 0.4. Solving for S here, we get 0.00030 is 1.132 molar. So one of the things that I want to mention to you here is that the common ion effect reduces ionization. We know this from Le Chatelier's principle. If you take this solid and dump it into 0.20 molar lead nitrate, again, lead nitrate is lead ion plus nitrate ion, the common lead plus Pb plus 2, that common ion, will shift the equilibrium this way towards solids. So the common ion effect, essentially what it's doing is that it's shifting the equilibrium towards the left-hand side, towards more solids, less ionization. So less ionization when you have the common ion. In this specific example, the common ion is lead plus 2.